Hi, everyone. So thanks so much for coming along to this Journal Club event hosted by ValleyDAO. We are a decentralized science community, and our focus is on sort of enabling fairer access to synbiotechnologies through our sort of funding and community-based IP model. We started this Journal Club because we think it's really cool for people to get access to ask questions and talk amongst themselves about scientific research. And this is why we host this and we post it on YouTube. Thanks so much, Alid, for joining us today. You are CTO and founder of DeakinBio, and you produce sustainable ceramic tiles. And today we're going to discuss extraterrestrial constructions.
Yeah, thanks very much for having me, and thanks very much for the introduction. So in this talk I'll be talking about a recent publication, StarCrete, starch-based regolith biocomposite for extraterrestrial construction. But first, just a little bit about us. So I'm based in the Future Biomanufacturing Research Hub, which is a UK-based National Biomanufacturing Accelerator. We're based in Manchester, in the Manchester Institute of Biotechnology, this lovely building here. And essentially what we do is try to coordinate UK and academic industrial biomanufacturing capabilities. So we're trying to kind of bridge the gap and trying to facilitate the transition to like the bioeconomy, largely by doing kind of tasks and jobs that industry doesn't really want to do because it's kind of too expensive for them, and also things that academics don't really want to do potentially because it's not of interest for them. And we largely operate through industrial partnerships and various research programs. We're a hub and spoke model, so our core is in Manchester where I'm based, and then we've got several spokes at other universities and institutions around the UK. And we focus on 4 key sectors, which are pharmaceuticals, value-added chemicals, advanced synthetic fuels, and my area, which is engineering materials. So yeah, trying to basically use bio-based manufacturing routes to produce these substances in these categories. And another big focus of ours is developing novel microbial production routes, which again is something that industry would quite like, but doesn't necessarily want to invest in it themselves. So we're trying to develop these various new host organisms which have the potential to be much more efficient or have various advantages in some ways. And we also are developing in silico design tools, automation and state-of-the-art analytics, and that is a national capability which is open for any institute in the UK to potentially access. So about this paper, so essentially, the challenge we're facing is that any kind of off-world habitat on like the moon and Mars is going to need very thick walls and ceilings. Basically, space is full of radiation from the sun and from the galaxy. The Earth is protected by a magnetic field, global magnetic field, which deflects all this radiation. But any habitat on the moon and Mars, you're going to be perpetually bombarded by this radiation. So any kind of long-term habitat on the moon and any trip to Mars, which will have to be relatively long-term, about 500 days at the very least, just because of orbital alignment windows, is going to have to be a sustained presence. So we're going to need habitats with radiation shielding capability. And the most feasible way of doing this is basically just building your habitat with shielding of regolith, at least 1 meter thick, to protect you from that radiation. And also micrometeoroids, because there's no atmosphere on the moon and Mars. Any kind of small pea-sized micrometeorite which would burn up in the Earth's atmosphere would just come down like a bullet, going several times the speed of a bullet, and potentially tear through your habitat, which would be good. So you need shielding against that as well. It's not feasible to transport bulk construction materials from Earth, so you can't really ship up loads of concrete because that's going to weigh a lot, and that would cost a lot to ship that up. So we need to use as much as possible in situ resources. It's called in situ resource utilization. And we also need to minimize energy and water use. So there are some concepts out there where you can produce these construction materials, but a lot of them use huge amounts of energy. So for example, some concepts you literally melt the regolith, the dust, into a lava and cast it into bricks, which works well, but you just need a vast amount of energy. So that would mean you'd need to bring loads more solar panels or nuclear reactors or whatnot. which would add extra cost and complexity and kind of offsets the benefit of using in situ resources. And some concepts use a lot of water as well, which is going to be an extremely scarce resource in these environments. So we want a solution that doesn't use too much energy and too much water. We also need to integrate systems. So what I mean by that is we don't really want separate standalone systems that do one thing and that's all it does. So if you are living in a very small apartment and you want a sofa and you want a bed, you'd probably get a sofa bed. That's like the sofa and bed system integrated into one. Exact same concept in like a space environment. So you want to integrate as many systems into one, have kind of a Swiss Army knife type thing. And probably the best example of this are hydrogen fuel cells, which were it was a technology massively spearheaded by the Gemini and Apollo programs. And essentially NASA saw this potential technology and were like, hey, it'd be great if we could turn hydrogen oxygen, which we're going to have anyway because it's rocket fuel, into electricity, so we don't take batteries, but the byproduct is water, which the astronauts can then drink. So that's like three things integrated into one. You don't need batteries, you don't need so much water, and you've got the rocket fuel anyway. So they really spearheaded that technology, and we need to do the same thing for future trips to the moon and Mars. We also need to minimize cost and risk. So essentially cost is proportional to the feasibility. If things are going to, if a mission to Mars or moon is going to cost too much, it's not feasible, it's going to get cut. Once people start thinking of it in terms of what we could spend that money on otherwise, schools, hospitals, whatever, if it's very expensive, it's not going to be very feasible. But risk is also inversely proportional to the cost. So we obviously want the mission to be as low risk as possible. But if you minimise the risk, you inevitably have to have lots of backup systems to add mass, to add cost to the mission. And yes, the cost is also proportional to the initial mass to low Earth orbit. So getting into orbit takes a lot of energy, takes a lot of rocket fuel. Getting from orbit to other places like the moon and Mars doesn't take so much energy. So we want to minimise the initial mass we have to take into low Earth orbit. So because this is a biotech interest group, I thought I'd give my case for biotechnology in space. So basically, I'm of the belief that we could use biotechnology to considerably simplify mission architecture and make missions to the moon and Mars more feasible and cheaper. So, for example, Mars, we know it has all the necessary ingredients for life. It has trace amounts of water, has all the nutrients, has sunlight, has carbon dioxide, and that's one of the reasons we want to visit there, to see if there was, is any remnants of past life. So that means we can potentially support, life with all the stuff we find there. And we also know that crewed missions will, by definition, have to have the capabilities to support life. So, we'll have to have ambient conditions, room pressure, room temperature. So that means we can support, bioreactors if we can support crew. And it also opens the possibility for quite a lot more integration of systems, as I mentioned before. So, for example, if we took algae photobioreactors to the Martian surface as part of a mission, we can take stuff we can get from the Martian surface itself, so carbon dioxide, nitrogen from the atmosphere, water from the regolith, trace elements and sunlight, and produce food. So algae, something like spirulina, is very efficient at putting on biomass that can be eaten, but also produces oxygen. So that's like two systems. We don't need a separate oxygen production system, food production system. We can have two in one. But also algae can be used to make biofuels, and also could be engineered to produce various other types of fuels, which is something we're looking at in the FBIH. And when you land on Mars, you want to land as light as possible. So you want your ship to land like an empty fuel tank, and then you want to produce your fuel in situ if possible. So algae could be a way to do this. But also you could engineer algae through synthetic biology, through biotechnology, to produce useful substances for pharmaceuticals. So if you're going to send a crew to Mars, you have to, to lower the risk, you have to take medicines and anything they might potentially need. This is going to add a lot of cost and complexity, because you're going to have to take lots of pharmaceuticals that you might never actually need, but just in case someone gets ill, you're going to have to take them. But if we could engineer, if we took these algae photobioreactors or some other kind of biotech bioreactor, we could potentially, if someone gets ill, NASA could work really hard to come up with the plasmid, the DNA sequences to produce pharmaceuticals that are needed, or they might already exist in the literature, and then they just kind of send that email to the Martian base, and then they can do the biotech. They could produce the DNA. By the way, I'm not a biologist or biotechnologist by background, so sorry if I seem a bit ignorant in some of the terminology. But essentially, you could potentially biomanufacture pharmaceuticals. That means you don't have to take them all the way to Moon and Mars, which should, essentially save a lot of mess and a lot of cost off the mission, simplifying things. And you can also make materials through biomanufacturing, which is kind of more my area. So yeah, you can make bioplastics and produce things, PLA maybe for 3D printing or something. But the thing I'm particularly interested in going to talk about in this talk is, can we use biotech to produce construction materials, which we're going to need vast quantities of? And could this technology benefit Earth? So one of the big reasons we want to push the boundaries and kind of get to the Moon and Mars is because there will inevitably be technological benefits and offshoots which we can then utilize on Earth. So if we can come up with a way to produce a construction material like concrete through bio-based means, out of necessity for human habitation and survivability on Mars, that could potentially be then translated to Earth, and then we could have potentially a bio-based alternative to concrete, and concrete is a really big emitter of carbon dioxide emissions, 8% of global carbon dioxide emissions. So that would be a really good technology to develop. So just a bit of background work. So we started doing, producing recombinant proteins for adhesives. So historically, proteins were used as glues. So if you've ever heard the terminology, the phrase "sending the horse to the glue factories," because horses, when they got old, they'd be sent to a glue factory, and their skin, the collagen essentially from their skin, their connective tissue and their bones would be boiled down, turned into a glue. Egg whites and stuff, the albumin was also historically used as an adhesive, and still is in some instances. So he thought, well, if all these kind of plain abundant proteins are naturally quite sticky and adhesive, can we engineer proteins to make better glues for the post-petroleum age? Essentially, we need to stop using oils. Can we go back to how we used to make glues, but kind of with our kind of modern understanding and tools of synthetic biology? Can we produce better adhesives through biology? And we focused on spider silk proteins. The spiders produce very sticky silk-based glues on their webs, so when bugs fly into webs, spiders have blobs of glue and it sticks the bugs on. So we were looking at a range of proteins, including spider silk proteins, and then doing some formulation optimization with some additives. The idea was to make a protein-based glue. But we surprisingly found BSA as a control experiment, so bovine serum albumin, cheap protein used for loads of control experiments, have actually performed better than spider silk at sticking glass together. So we were scratching our heads about this, but then we realized that animal blood was historically used as a glue, and albumins in eggs, that's the main protein component of eggs, so it actually kind of made sense. So then we thought, if we can stick glass together really well, could we use BSA as a binder, so a glue to stick together particles in lunar and Martian regolith to make a biocomposite, a concrete-like material. But we found that the work had already been done. So people had literally taken BSA, mixed it with Mars dust and moon dust, and made material. So it's gutted. We'd been beaten to it by someone who'd done it years ago. But then we thought, well, they'd use BSA, and it's not actually very feasible to take cows into space with the BSA. And if you're to produce it recombinantly, you are going to need to take bioreactors, extra mass, use a lot of water, and there will be waste associated with that. But we know humans are going to be present anyway, by definition, any crude Mars. So we thought, can we use the human equivalent of bovine serum albumin, human serum albumin, as glue instead? So it was kind of a joke at first, kind of a jokey tongue-in-cheek paper, but then it was well, actually, maybe there's some grounds to this. So so this is the protocol we followed. It's very simple. It was kind of just a kind of side experiment, not my main project, but it turned out quite nice. Essentially, we just dissolved some human serum albumin in some water, infused it with this simple setup with some regoliths, in this case it's moon dust, dried it out at 65 degrees, and then we were left with this bioconcrete-like material. And humans will actually produce up to 25 grams of human serum albumin per day. That's quite good production. If you compare that to a bioreactor producing protein, we're quite efficient bioreactors. So if you're going to have to take a whole bioreactor to Mars, why not just take another human if we're going to produce this much anyway? It's present in blood plasma at a concentration of 60 grams per litre. So again, if you had a bioreactor, it's going to be very tricky to get that concentration of output of protein. Investigating the mechanism, we were looking at denaturation of the protein. We actually found that urea, which is a common protein denaturing, actually improve the mechanical properties by up to 3 times in some instances. And the great thing about urea is it's the main solid component of urine, which we're gonna have abundant on Mars anyway. So yeah, that was a really nice finding, and we eventually found that we could get compressive strength up to 40 megapascals, which is really good, and it simplifies mission architecture. You don't need so many systems, and yeah, you can just basically produce materials out of humans and regolith, which will be really good. Obviously, has some drawbacks, so limited production. It's limited by the number of crew, risks human well-being, which isn't good, and you can't pre-deploy habitats. So obviously you need to have shelter before people get there. So there's some serious drawbacks, which means it's almost certainly never going to work. So in this paper, our aim was to essentially cut out the middleman literally. So instead of going via humans who would have to feed and using their blood to make regolith biocomposites, we thought, well, can we cut them out and just use food to make biocomposites? So we were thinking maybe gluten, which is used historically as a glue. That's where the word glue comes from, apparently, gluten. But also starch was used historically as a glue, and it's still used in Aboriginal tribes to glue feathers onto arrows, so it can make like a very strong glue. So this has all the advantages of human serum albumin, but the production isn't limited by number of crew. You can just grow more potatoes or rice or whatever. It doesn't risk crew health. And you can also pre-deploy it, so you want to test all critical systems before you send crew, so you want to be growing food anyway before the crew get anywhere near, if they're going to have to depend on it for their lives. So you potentially build your Martian habitat with starch before the crew get there, so have like a pre-deployed habitat. But someone had already done something very similar. We only realised this after we'd started the work, but they hadn't used it for regolith, they used it for sand, so this concrete paper. And this is the method here. It's quite simple. So we get regolith, so moon dust, Mars dust, we mix starch powder, we add water and we heat it, and then these starch granules burst. So if you've ever made gravy or custard, I don't know if you eat too much of that, but it's the same kind of process. It's gelatinization of starch. These granules of starch absorb water as you heat it up, swell it and burst, and it becomes this gel inorganic particle hybrid material. Then if you dry it out a bit and compress it and dry it out some more, then you get this StarCrete material. So that's the method. I do have a YouTube video here, but I'm just going to skip over it for now, but if you want to watch it, I can share that later. So the kind of core of the paper was method development, really, because essentially starch gelatinization is a very complex process. It depends on many factors like concentration, the pH, temperature profile. If it cools down, it can retrograde, recrystallize essentially. Enzymes like amylase in your spit can affect it, and there's all sorts of different variables just on the starch source. So if you get it from rice, potatoes, or somewhere, then it's going to be quite different. So yeah, starch is like 2 main different biopolymers, but these also differ as well. So because it was such a complex kind of system, and we were kind of starting without much ground to work on, we decided to go for a statistical design of experiments methodology. And if you don't know what design of experiments, it's a really useful technique. It's a bit like machine learning. So you use similar algorithms to produce models, and it will kind of tell you where to go in the experimental space, like how to optimize your system. But rather than using kind of random data sets, it tells you exactly where to do your experiments to get the most out of your data. So it's really great for just kind of maximizing the useful information you can squeeze out of your system. So it's really useful when you've got a complex system with lots of things going on. Really good for biotechnology. But the first thing we did was just screen different starch sources. So with different starch sources, they have all these different properties. But the main thing here is we just kind of looked at which ones behaved the best. Looked like potato starch performed the best. So we got quite high strength just off the bat, which was really nice and promising. The next thing we did was screen different additives. So essentially, we thought, what are the different additives we could get on Mars, and can any of these potentially improve the compressive strength of the material? So we tested a few different things. We tested urea, which we can get, as I mentioned before, from urine, a few salts, which you can get from the Martian surface, acetic acid, which you get from fermenting starch and other food, and saliva as well. And the reason for that is saliva was used with starch to make the glues I mentioned before to stick on arrowheads. So it has some effect on starch chops it up, which can potentially make it gluer, stickier. And then we made these materials with these additives, and then just kind of saw what the compressive strength was. And we found adding urea helped, adding acetic acid seemed to help. Adding magnesium chloride didn't help, but it had like an odd effect, so it kind of made it a lot kind of sticky and slimy. So we thought maybe we've just used way too much because this was a saturated solution. So we incorporated that into the design going forward. The next thing we did is called a differentiative screening design. So this is one of the first designer experiments, and basically this is a very efficient way to rapidly screen the effect of variables. So essentially, you've got all these different things that might have an effect, but you're not sure, is the compression force going to matter? Is the drying temperature going to matter? With this type of experiment, you can put lots of input variables in, and then you don't have to do that many experimental runs, and it tells you which ones are important, which ones are not important. Like if you're baking a cake and you had no idea for all these factors, you don't know if resting the cake or room humidity is going to matter, you can kind of screen the importance of factors and look for like interactions of these variables and see which ones are important, which way you want to go in the experimental space. It's a really useful method. 25 experimental runs, we get lots of data out. And what this experiment showed us was there was a couple of factors which are like really important. So basically, the gelation temperature, so the temperature we're gelling at, and the gelation time were like set too low. So it's like if you're baking a cake, but the oven temperature is too low and the time in the oven is too low, nearly all your cakes are going to not taste good because these factors are just kind of overriding everything. But that was really useful information to find out early without wasting lots of time doing lots of random things, then realizing, oh, the oven's set too low type of thing. And it predicted, so higher gelation temperature and gelation time would make things better. So that's what we did. So then we did another experiment called a central composite design. Just 9 experimental runs where we just looked at gelation time, gelation temperature, keeping everything else constant. And this helped us get from a compressive strength of about 15 megapascals up to over 50. So it really, really helped this experiment. And again, it was just 9 experimental runs because that previous experiment told us what to focus on. And it predicted that even higher gelation temperatures, so it's saying go even higher to get higher strengths, and higher gelation times would help. So that's what I did. What I didn't realize is that urea decomposes at about 150 degrees Celsius, and it produces isocyanic acid, which is a poisonous gas. It also produces ammonia, which I was able to smell, and I was like, why is it made ammonia? That doesn't make any sense. And I looked into it and I realized, oh God, it's producing this poisonous gas. It's actually a sensitizer, which basically means if I'm exposed to it again, I could get like a deadly asthma attack apparently. So I just need to make sure I don't do it again. So yeah, that's a lesson to be learned there, I'm sure. So the next thing we did is a custom design. And basically this is a correlation color map of the first experiment, the definitive screening design. And basically what it's showing is this white area. The definitive screening design is basically kind of screens for primary interactions, so your kind of main effects, if there's any kind of interactions. So basically it's kind of like screening very basic kind of interactions between like variables, and this whole kind of grey area, the more kind of complex interaction zone, it kind of just ignores that, so you get a lot of confounding, which is you can't unpick what is the complex interactions that are going on between lots of different variables. And that was 24 experiments, or 25. And then this custom design, it was 56 experimental runs, and essentially it gives you much higher resolution of the experimental space. So it picks out all the experimental combinations to get you the maximum amount of information from this complex experimental space. And by now there were fewer factors as well. So it's more experimental runs, fewer factors, but much better resolution. So it tells you a lot more what's going on in your system. So yeah, it was an 8-factor custom design, and essentially it gave us a lot of useful information. Interestingly, it showed us a lot of the additives that looked like they were initially going to be useful actually weren't useful. So adding urea after optimization actually didn't help. Same with acetic acid. The materials were stronger with 0 acetic acid. And interestingly, adding magnesium chloride did help, even though in the initial additive screening experiment, it didn't help because we just kind of overloaded it, but we carried on looking at it out of curiosity. But yeah, it gives us very high quality information about the system. And yeah, one of our samples was like over 70 megapascals with under compression. So it found one random combination, which was like a really nice area of the experimental space. We got like a very strong material out of that. Then we did one final custom design just to try and push the compressive strength even further. But essentially what we found was if we increased the magnesium chloride concentration even more, it went down. If we increased the temperature even more, and now we could do that because we weren't using urea anymore, so there was no poison gas being produced, it actually made the samples worse, less strong. So basically it kind of suggested we'd already found like the peak of that kind of complex experimental space and pushing the factors to even more extremes. It didn't help. We were at that peak of like the hell. So the main results in the paper were essentially just kind of a culmination of all this optimization, because that was kind of the important thing. We were optimizing for compressive strength, trying to get the strongest materials possible, because that was just kind of the thing we decided to focus on. And with MGS1, which is a Martian simulant, we got compressive strengths up to 71 megapascals, and we did, I think, 5 repeats, and there was quite low variance between the samples, which was a really good thing. It basically suggested that there weren't any nuisance variables affecting the results, and that's the good thing about doing design experiments. Is we screened out so many factors, it would tell us like if there's something that's kind of important that's kind of affecting you, so you can kind of rule out nuisance variables, which if you kind of don't do early on, you can kind of get like annoying variation in your results, and you don't really know what's going on. And when we translated to lunar Highland simulants, so moon dust essentially, it was even stronger. So we got up to over 90 megapascals in the compression. And just to put that into context, this is just a diagram showing comparing other kind of like technologies for potentially building on the moon and Mars. As you go along this axis, you need more material beyond unprocessed regolith. So you want to be down here. You want to use as much kind of raw moon dust, Mars dust, and as little kind of whatever else as your binder or whatnot as possible. And then obviously compressive strength, you want to be as strong as possible. So we're up here in this corner, which is low amount of binder to add and quite high compressive strength. And the colours represent energy use. So green is low energy processes, yellow is medium energy processes, and purple are like high energy processes. And obviously you don't want to use too much energy for reasons mentioned before. So ours is a relatively low energy process. There's no like high temperature sintering or anything. So we occupy a nice kind of sweet spot up here. So in conclusion, we found that starch is an effective binder for regolith biocomposites fabrication. It's a relatively feasible option compared to other technology options. So, for example, it's integrated with other systems, food and oxygen production. We're going to have to feed the astronauts anyway. So if we are growing potatoes, we can make food, we can make oxygen, and now we can make the construction materials also, so we don't need a whole other system doing that. Relatively high technology readiness. Some of the other technology options, they're kind of out there in terms of feasibility, and they're not that feasible essentially, and not a huge amount of energy consumption. The water can be recovered as well, so when you like hardening materials, it's based on dehydration, so you can put it like a dehydrator, recover that water and recycle it. Other technology options like Martian concrete or cement, they're hydration-based reactions, so like water kind of gets locked up permanently if you're making something like that. We do need to do further studies, so it's just a communication paper, so there's quite a lot more work that could and should be done just to evaluate its full potential, especially testing it in like simulated operational environments, so large heat swings, bombarded by radiation, and low vacuum is definitely something we need to confirm it will still operate under those conditions. And I think the main kind of thing from this is the technology has spearheaded sustainable construction materials on Earth. So Sara mentioned before, I've got like a startup now, DeakinBio, where we're doing like a related technologies to produce sustainable construction materials on Earth. So focusing on ceramics. So similar technology, biocomposites, where we take like a protein or biopolymer as like a glue, as a binder, and combine it with an inorganic substance to make alternatives to concrete on Earth, or ceramic materials that don't need to be fired. So that's the main conclusion I think to take away. So thanks very much for listening. I'd like to acknowledge all these people and happy to take any questions.
Thank you so much for this presentation. There are many very interesting talking points here, I think, including design of experiments, sort of feasibility, etc. So we can start taking questions if anybody has any questions, and if not, then I'll start.
Yeah, it was very good. Thank you. So I'm one of the ValleyDAO people here. I personally have a background in physics, so I'm wondering, are you working with physicists at all, or what does their contribution look like? Well, if yes, what does their sort of contribution look like here?
So I'm not actually working with any physicists. So a lot of this work was done over COVID lockdown, and in fact I did it in my basement just because it was a type of work I could just do at home. So that was actually really important. My startup as well, it was like something I could do at home, so I did. But that kind of meant I was isolated, obviously a lot from the scientific community and collaborations and stuff. And I only recently got into space, like over the COVID period. I would really like to work with physicists, especially in areas of radiation shielding potential of the material, and kind of further kind of analysis and characterization, I suppose, would be good. But I'm kind of not really in that kind of scientific community, so it would be great to find people who'd be interested in working with me there.
Right. Okay. When in some of these illustrations, I see buildings that have pointy features, and when physicists think about these desolate environments, they always think about things like friction and what sort of effect that can have, and on things. So ideally you would have round things as round as possible. But I remember when I was still in high school, I did some sort of a competition, and we were supposed to design habitats, Mars related, and we came up with designs, and always you would see designs that are the best are the ones where they had the roundest possible constructions. And so it looks like physicists definitely should be involved, especially when it comes to these illustrations. It looks cool though.
So to be honest, these illustrations I've just kind of picked off the internet. I presume they're artist impersonations. This one at the bottom is from ESA, so I think that's a more feasible concept. And it's rounded, of course. But I've heard the similar thing. Essentially, we'll have to live in hobbit holes or something, where it's a relatively rounded structure for sure.
I think one question I have is, when you are inputting data into these sort of design of experiments, experimental spaces, in terms of sort of the starch, where the starch comes from, how feasible do you think your current prediction, your current sort of starch source would be in space? Have you spoken to people, people who are researching into nutrition in space, for example, and what do you think would be a feasible food material, the starch source? Sorry.
That's a really interesting question. So there's a huge amount that could be done in terms of selecting different kind of breeds, or even genetically engineering the plants to change the type of starch that's done. So for example, you have ordinary cornstarch, and then it's been bred to death to produce waxy corn, which I think has a really high content of amylopectin. So you can basically breed or genetically engineer the plants to be optimal for nutrition, which you definitely want to have in an off-field habitat. But you could also similarly probably have like some set aside which are engineered for optimal construction properties. So you need to use a lot less. And then because they're plants, you can just kind of keep that DNA or keep the seeds and then kind of change the proportion you're growing for whatever reason. And because food is like a mission critical thing, which is basically if that system fails and the crew could potentially die, you want to have redundancy, you want to have backup. So you'll be producing like a surplus of food anyway. So you'd want to have, you'd be producing it more anyway, and then under ordinary operating conditions, you can like produce that surplus to make the construction material. In terms of like nutrition, something we're looking at, is the algae. So NASA's already interested in that because it's essentially like a superfood. It's super nutritious. It grows really fast. It's packed full of like protein and chlorophyll and other kind of like nutrients that are good for your health. And it has the other advantages as well. It can be engineered to do things. It produces oxygen really efficiently, more efficiently than plants. So we're looking at if we can make construction materials from that, if that's something we're going to be producing anyway. But in terms of starch, it's quite flexible. So if, for example, potatoes aren't feasible for whatever reason, and I don't know, the aquaponic or whatever system you have for growing food is much better with rice, you could still do it with rice, but you might have to like do some engineering to optimize like the properties of starch to get it as good as possible.
Or change the other experimental parameters as well.
Exactly,
But I wonder if you see a situation such as the current one we have, which is this, food versus fuel debate. Do you think that's something that it will actually be extrapolated onto extraterrestrial systems?
Yeah, that's a really good point. The food versus fuel debate. That's another reason why we're kind of shifting focus to algae right now, because essentially we're going to be growing algae on Earth for like biofuels, and like 50% of algae's like mass is like oils and lipids, which you can grow put as fuels. And you don't necessarily have to use farmland to grow algae. You can grow it out at sea. You can have tall buildings. You can grow it vertically or whatnot. So we're trying to think of that from the outset. So, for example, you're using starch. If we translated that technology to Earth and actually took off, it could affect the human food supply chain. About 40% of starch is already used for industrial purposes. It's using cardboard manufacture, so it's already kind of being used a lot. But if there was a whole other kind of demand on it, it wouldn't be a good thing. In terms of outer space, the use of starch and the food or fuel debate, food or materials debate, I think astronaut kind of health and well-being will always be the number one priority, and that's why the human blood method is never really going to fly. But I don't think astronauts are ever going to go hungry, but you'd want to be producing, as I said before, a big surplus of food anyway under ordinary conditions, just in case there's a disaster and some of your plants die, or there's crop disease, or there's lower than expected yields. But the astronauts' kind of food will probably always come first, and you'd probably already have at least a large part of your habitat in terms of radiation shielding already built before the astronauts even get there. But for habitat expansion, you'd want to be producing a surplus, and that would be available.
All right, I can go. So when you talk to organizations like NASA and ESA and some of the other ones that are that have the funding and the expertise to actually implement some of these things, how fringe or how mainstream these things are in their heads? I'm just trying to think of the timeline. Is that a very speculative? Is that going to be a very speculative answer, or?
Yeah, so NASA in particular is very interested in developing construction materials for the Artemis program, the upcoming Artemis program, sending humans to the moon for sustained periods. They need to solve that problem. Actually, on the moon, it's not such of a big deal because there's no atmosphere, so you can just kind of pile it up and the regolith by itself will be okay. But we want to develop and test technologies on the moon to take to Mars eventually. So NASA's very interesting, and like a few years ago they had this thing called the Centennial Challenge, and the theme for that year was developing 3D printed construction technologies for building habitats on the moon and Mars. But a big part of that was the actual material you're going to use for 3D printed construction. The blood stuff they didn't want to touch, at all. I don't think they just wanted to be associated with that, which isn't too surprising. I did do a couple of talks, like UK Space Agency, but essentially we weren't really taking that blood one very seriously. But the starch one, it's still quite new, so we haven't actually engaged very much at all, aside from the odd conference where I go around with a chunk of it and show some people who are in ESA, for example, and they're like, oh wow, I didn't know about this. So they seem quite interested. But yeah, the first one, because it was blood, they didn't really want to touch. So I'm hoping this one is kind of us being more serious about it, and they'll actually be genuinely interested. But it's a bit early, it's early days at the moment, so hopefully in a few months' time I'll get some emails from NASA people who might be interested in exploring it further.
Yeah, we should definitely popularize this more. What about private institutions? So startups. I mean, are you aware of startups? I'm sure there are startups in this space that are actively working on things like these, right?
Yeah. So the startup I have is pursuing this type of materials, and there are a few other startups in this space. A lot of them, like biomedicine, for example, are pursuing engineered living materials. So that's where you use kind of living, often engineered microbes to produce construction materials. So it's a different mechanism, producing biocement. So it mineralizes calcium carbonate to fuse particles of aggregate together. So they're in the same space, but a different technology. In terms of composite materials, there are a few others, but it doesn't seem like it's a very active space. For example, mycelium-based materials it's got a lot of interest. There's loads of people working on it, and there's lots of money flowing into that. Spider silk-based materials, I think Bolt Threads has had something like $500 million worth of startup funding. It's one of the most funded startups in the world. So there's lots of interest in similar areas, but these specific materials, there's not much interest yet, but we're hoping we're just kind of ahead of the curve. And we're applying for a few things now, and hopefully we'll get some traction and some momentum going there.
This is a bit of a it's a question. Where did you get your moon dust from?
So there are a few companies about that produce scientifically accurate moon and Mars dust simulants. It's not actually from the moon or Mars, but basically because we've taken rocks back from the moon from the Apollo programs, they've been analysed, and we can now generate simulants based on just kind of Earth-based volcanic rocks grinding up into the right consistency. And the same with Mars. Mars's dust has been analysed by rovers, so that's been analysed, and basically there's companies out there now. I think a lot of them are non-profits, just kind of affiliated with universities, that will produce simulants and then sell them generally to non-commercial entities. A lot of them have a rule you can't just buy it and then sell it off to people as moon dust and make loads of money out of that. You have to kind of use it for research or something serious.
Is it expensive?
Surprisingly not that expensive. Again, I think because they're kind of non-profit, I think they could charge loads for it if they wanted to, but I think some of them are non-profits. They just kind of undercut anyone who's trying to rip people off. So yeah, for a kilogram it might be $50 or something. So you can make a lot of material samples out of a kilogram. So yeah, $50 is nothing really.
Awesome. So, if there's no other questions, thank you so much, Aled, for this talk, and thank you everyone for joining us.
Thank you very much for hosting me. It was a pleasure. Nice to meet you.